Yeah, the loud and clear.
Okay, good. Good evening, everybody, and welcome to the second session, which we will start today about the 5 ideas that change our understanding of the universe in the last century. So this is part 2 of a 2-day session. At the end of yesterday, we summarized the 3 topics we talked about yesterday. First was our past understanding of the universe in the 19th century. So we tried to get understand what do people think about the universe before 1900. And then the 2 great ideas which revolutionized our idea in the 20th century: the size of the universe expanded in a sense that our idea of the universe became much larger than what it really is, what it was in the past. And then we also realized that the universe was expanding and that it had an origin. And then if we extrapolate back in time, we could postulate that it had an origin called the Big Bang. Today, we will take up the next 3 ideas. That is, how do the elements which make up the Earth and life on Earth, where do they originate from? The second, we will talk about the end of the universe. And the third topic we will talk about is the discovery of extraterrestrial planets and the signatures of life in outer space. For the questions that were asked yesterday, I briefly tried to answer them in text and I put them up. I won't have time to talk about them today. I will try and include them within today's lecture. But given that we have 3 topics today and it's quite a lot to cover, let's get started. Good. Let's go to the next page. Okay, let's start with the origin of the elements. I mean, I put 2 quotations from Shakespeare. It is the stars above us that govern our conditions. And then another one: the fault, dear Brutus, is not in our stars, but in ourselves. We always have realized that in some way, the stars govern life on Earth. I'm not talking about astrology, but somehow we are intrinsically connected with our life here on Earth is intrinsically connected with the stars. And today we will see how that is. So let's start immediately with the question which we saw yesterday was stars. If we look up at the night sky, we realize there are a large variety of stars. As we saw this plot yesterday on the left, stars have various types of luminosity. So on the y-axis I point out over here, stars have various types of luminosities. If the sun is a luminosity assigned 1, then there are stars 10 times, 100 times, 1,000 times, 10,000 times, and there are stars even dimmer than that of the sun. And the question which people have been asking for, at least at the start of the 20th century, is how do stars fuel their power source? What is it within the stars that allows it to shine so much light? Why are there so many different types of stars? How long do these stars live for? Are they born? How long do they live for? And how do they die? And finally, what is that intrinsic connection between the elements on the Earth and the life of a star? Now, let's look at the star which we can study the most, and that is our sun. The sun is really huge. It's about the radius of the sun is about 100 times the radius of the Earth, and the radius of the Earth is about approximately 6,000 kilometers. Okay, the mass of the sun is also very huge. So you can think of it as 2 times a large number with 30 zeros in kg. 30 zeros. It's really a huge quantity of material. The sun is also very hot. It has a temperature of about 6,000 Kelvin, so about 6,273 degrees. And it is an enormous power source. Now, from our basic understanding of physics, we realize that because of its huge mass, there must be two forces which are acting on it. Certainly, the mass has gravity, so the gravity is pulling it inside, so it's bringing it towards the center. But there must be another energy source which is actually propping it up, and the sun is, as it is, quite stable because these two energy sources, gravity and the force from the other energy source, is in perfect balance. And of course, this other energy source is also giving out all this light, all this power in the form of light. What is a possible energy source which could power the sun? At the start of the 20th century, people began asking this question. So they said, okay, can you burn? How much wood do you need to burn to power the sun? How much coal do you need to burn to power the sun? Or dynamite, TNT was invented at the start of the century. Would that much quantity of TNT be enough to power the sun? And they realized that all their answers didn't make sense, that none of the sources which they had, which we have on Earth as power sources, was able to power the sun and allow it to shine as it shines for the lifetime of humankind. Let's go a bit ahead. And then the other question which people have been asking is, okay, what is the origin of the element? So what I'm putting forth for you here is the periodic table. And as we know, something which we learned in school, the periodic table is a systematic description of all the elements in nature, starting with hydrogen, helium, then we have carbon, nitrogen, oxygen, silicon, which is the basis of all our electronic products, and a whole bunch of other elements. And on this periodic table, you see that each of them, they are numbered, and the number is the number of protons, which are there in their nuclei. So the question can, how are these elements formed? Where are they formed? Were they formed right at the beginning of the universe? Or were they formed much later in time? And the other question, so just to show you what this means, is that the hydrogen would just have one proton. The helium would have two protons, but it also has another object called the neutrons. Carbon would have 6 protons. Silicon would have 14 protons and a whole bunch of other neutrons with it. So the bigger the element comes, the bigger it grows, the more it acquires protons. So one question is, where is the origin of the elements? But there's another question is, not only do we need to explain the origin, but we need to explain the abundance of these elements. We know that if you look at life here on Earth, we know that most of it is made up of oxygen, okay, hydrogen and oxygen. Then we have a lot of carbon in our bodies, and we have a whole bunch of other elements, nitrogen, calcium, phosphorus, and a whole bunch of other elements here. But if we look at the full of the Earth's crust, we see a whole other set of elements. It's like silicon, aluminium, iron, which form the Earth's crust. And the question is, why are these elements distributed in this particular way on Earth or on life? And what gives rise to these abundances in the elements? So this is the second question people were asking at the beginning of the 20th century. Now, around 1920, Arthur Eddington, a famous astronomer at the University of Cambridge, who was keeping abreast with the various developments in quantum mechanics, suggested for the first time that the only way you can power the sun is a process which is called as nuclear fusion. Now, what is nuclear fusion? Nuclear fusion is the fusion of, you take two very small nuclei, let's say hydrogen and hydrogen, you bring them together, you combine them to make a bigger element like helium, and in the process, a large amount of energy is released. Okay? So here we have, in this figure, I'm showing you two elements. One is, here they're called as deuterium and tritium, and they are combined. Okay, both of them are actually various types of hydrogen. They are combined, they are fused together, and they produce helium. Now, nuclear fusion, I think we're all familiar with this. It's the basis of nuclear energy. There are two types of nuclear, fission and fusion. Fission, where you break an atom. Fusion is when you fuse an atom. So Arthur Eddington suggested that nuclear fusion was the source of the energy on the sun. And then later on, a lady working at the University of Harvard, her name is Cecilia Helena Payne. She was the first lady, in fact, to get a PhD in astronomy. She was studying the theory of an Indian physicist named Meghnad Saha, who actually worked towards studying the ionization of elements in the new theory of quantum mechanics that had just come up around that time. And she combined these, she looked at these observations of the sun. She looked at the way people try to understand what are the various elements within the sun, the spectrum of the sun. And she, using the theory of Meghnad Saha, deduced that the spectrum of the sun is very different from a possible spectrum of elements here on Earth. What does this mean? She says, most of the elements on the Earth, okay, seem to be present on the surface of the sun. But there seems to be something more in the sun which is not present on the Earth. And that, she found, was hydrogen and helium. The sun seems to have a huge quantity of hydrogen and helium within it, on its surface, and that is not present on the Earth. And everything else is present on the Earth. And based on these facts, she deduced that maybe the sun was fully made up of hydrogen and helium. And that if there are so many stars like the sun, as she could see all these stars, then the universe is predominantly made up of hydrogen and helium. And this was her theory, which she proposed in 1925. And she was very close to the truth. So in today, we know, and from most modern understanding, that in fact, the universe is made up of 73% hydrogen, 24% helium, and everything else is a very small fraction. And this tells us that the large amount of material in the universe is hydrogen and helium. And the thing which powers the sun is this theory of nuclear fusion, where hydrogen and helium combine, fuse together, and release a large amount of energy to power the sun. So let's look now briefly over this from 1920 onwards, right up till about 1950, astronomers tried, with this knowledge, tried to piece together how stars were formed and how stars lived and how stars died. And I will quickly walk you through that procedure in the next 5 minutes, okay? So the first thing that people realize is stars are born, and we can see stars being born, and I'll show you this in a minute. And stars are born in huge clouds of gas. So there is this huge clouds of gas in the universe. I'll show you in a minute. And these are called as stellar nebula. They look very colorful. But it's only diffuse gas. And this huge quantity of gas, due to gravity, starts slowly contracting. And as it becomes slowly contracting, it gets hotter, it gets more hot. And finally, it ignites and becomes a star. Okay? So when it becomes a star, it starts then converting hydrogen to helium, starts fusing its elements. And there are different types of sizes of stars. We will come to this in a minute. And they'll be like an average star like our sun, and our sun is very average. Or you could have a very massive star. And for the most time of its lifetime, the star lives in this phase, which we will call as the main sequence. Okay? It lives for a long time. And then when it finishes all its hydrogen, or when it finishes all its helium, it suddenly changes its shape and its color. And it becomes either a red giant or a red supergiant. You'll see this in a minute. And then finally, when it has no longer hydrogen and helium to burn, it's burned everything else, it dies. And that's the death of a star. And there are various ways a star can die. It can either explode, really explode, in two forms. If it's a small star, it explodes into something which is called as a planetary nebula. And if it's really big, it explodes so far that it almost, the night sky will suddenly look very bright. It's like suddenly a star in the night sky would become so big, it becomes like a million times more brighter than our sun for a brief amount of time. And finally, after it explodes, there is a small, what is called as a remnant left. And they can be something called a white dwarf, another small type of object. It could be a neutron star. It could even become what is called as a black hole. So this is the lifestyle of a star. And this is like in a very cartoon form. Take gas, start compressing it, ignite it, burn it, finish up all its material. And when it finishes its material, it slowly begins to die. The death could either be violent, like a supernova, or it could be a little more moderate death, planetary nebula. And then once it dies, explodes, the remnant also depends upon the size of the initial star. To get this in a little more detail now, this is like a much more complicated. Of course, the story gets more complicated once you look at the details. But I will not get into this detail, but it's the same thing. You have the birth, you have a molecular cloud, a nebula. It slowly contracts to a protostar. So it becomes, slowly starts contracting, and then it forms a star. There are various types of stars here. A high mass star, a low mass star, a very small star. And then it lives for most of its time on this main sequence. Then slowly becomes, when it finishes, it starts like, think of like your motor as your car is moving and your petrol is getting over. It starts sputtering. This is what happens. A red giant is like a sputtering, dying star. And then finally it explodes. And then there are various other effects which happen once the star fully explodes and dies. Okay? So this is the birth and death of, and this we kind of piece together slowly over the last century. Once we basically understood that stars burn, provide the energy by fusion, quickly things came back into place. And with large number of observations, they were able to put this together. Let me show you now a picture of a molecular cloud. So this is a molecular cloud over here, as I said. This is where it's full of gas and starts contracting and stars begin to form. Here are some pictures of the most famous gas clouds we have. This is the Horseshoe Nebula. And really what you're seeing here is the birthplace of stars. It's all this gas and dust here. This is not an artist image. This is like reality. And within these points, where you can see these sharp dots over here, here, and here, you see stars are being born within that gas. They start getting to ignite. Similarly, probably less colorful, but equally powerful are these gas clouds over here. And again, stars are being formed right in their centers of these gas clouds. Now we have understood this. We have finally pieced the puzzle. In our sun and in all stars, they are very massive. Gravity is pulling it together, but something is pushing it apart and giving its energy, and that's fusion. Okay? And fusion slowly makes much larger elements, like from hydrogen goes to helium and releases large amounts of energy on that. Okay. Let's now ask the question, what is, how long do stars last? So we're coming back to this diagram which we saw earlier. Stars have various brightnesses. So they can be much more brighter than the sun, or they could be less than the sun. And they could have various temperatures. Stars over here, the brighter stars are more hot, That means they are really, really hot. And stars which have lower luminosities are really cool. Okay, so most stars live on what is called as the main sequence. So they live on this. When they start finishing their fuel, they start sputtering, as I was saying earlier, and then they start moving off here and become giants or supergiants. But they live most of their life over here. Now, it's very interesting that depending upon, I don't know, so why do you have different types of stars? So basically, think of this gas cloud, which we saw earlier. So this was this gas cloud over here. And slowly, this gas cloud is contracting and is actually now forming stars. And what actually happens is that, so it actually collapses into different sizes. It kind of fragments into different sizes. I don't know if you give you a classic experience. Suppose you're on the, there is, you throw water on the floor, okay? And as you throw water on the floor, you realize the floor is wet, but the water kind of accumulates into various kind of puddles. And if you actually look around, you will see there'll be puddles of various sizes, one big, one small, one big. And the reason why this is because there is something which is pulling the water together. That's called surface tension of water. But it's the same experience over here. As the gas is contracting, and it fragments due to gravity, and you get different sizes. So you have large sizes and you have small sizes, and they start burning up. But the strange thing is that the stars which are bigger burn brighter. Stars which are smaller burn more slowly, and therefore they give less light. But there is also the fact that the more brighter they are, so I would like you to look at this table, the more brighter they are, so think of the sun is like 1 solar mass, the more brighter, the more massive they are, like 60 or 30, the less they live. So a star which is like the sun will live for 10 billion years. Our sun will live for 10 billion years. Just to remind you, the universe is about 13.7 billion years. But if you just have a star which is 10 times the mass of the sun, it lives for much less, to me 32 million years. And if if the star is even larger, 60 times, it lives even shorter, 3 million. Classic example of this from Daily Intuition. You are riding your latest Kawasaki bike, okay? And you know that you can drive at an optimal speed where you can use your fuel to the best and really the maximum and the best velocity to travel at that optimal fuel consumption. Let's say you accelerate really hard and you're moving and you're traveling much beyond the speed limit. You know that you are traveling now much faster, but you're also burning fuel much faster. And you realize that in a very country where petrol is very expensive, like India, you realize that if you travel faster, you're going to use up and consume most of your fuel very fast. Stars are pretty much like this. The bigger they are, faster they burn, and they consume their fuel very fast. Okay, so this is the reason why the lifetime on this sequence depends upon how fast it consumes. So these stars over here will last really long time, as long as the age of the universe, 13.7 billion. Well, these will last within a few million years, and they will soon will die immediately after that. So once we understand this, now I will show you the death of a star. So once the star becomes a red giant, explodes, this is the end product. This is what you see now are massive explosions of stars. Over here, you see a planetary nebula. So at the very end of our lifetime of our star will become a planetary nebula. It will be it just throws out a lot of material out there, but it will not be a very violent explosion. Stars which are much brighter, much bigger, will have what is called as a supernova. And this will be a massive, on the left here, the Crab Nebula is an example of a massive star which exploded and threw all this material out there. This is the example of the death now of a star. So now let's go back to the periodic table. So we realize that in essence, most of the star material on the periodic table is actually created in stars in their various phases, either as they burn or as they become in larger stars, in smaller stars, or finally when they die. And this theory was developed by a large number of people, starting with George Gamow in around the 1930s, and was more or less in place by 1954. By 1954, we looked at this periodic table and we kind of knew which element was created where. So for example, if you look at this table over here, it's, hydrogen and helium were almost created at the very beginning, around where the Big Bang. Lithium, barium, and boron were created with something which is called cosmic rays. I haven't really done that. Most of these elements in green, as you can see over here, were created in large stars. But the elements in yellow were created in small stars. So our sun is producing carbon, nitrogen, oxygen, a bit of sulfur, a bit of neon. And then finally, when stars die, all the heavier elements are being made. So in that grand supermassive, super explosion of supernova, very violent, all the heavier elements are made. And there are, of course, some elements which are totally man-made. We have made them in our laboratories. So finally, the elements on Earth are basically, most of them, 95% of them, are actually made in stars. And we can almost say that most of the heavier elements are the ashes of stars burning, or what we would like to call as cosmic dust. Everything we have here on Earth has been made in a star at some time in the past. Okay, so this is the one element. This is one of the greatest discoveries of the 20th century, to understand how stars live, how they form, they live and they die, and how do they produce the elements which we know in the universe and on Earth. Let's now try and put this in place. Let's try and understand this, what this means. What are the implications of this? So yesterday I showed you this figure of the evolution of the universe. Let's concentrate on this part here first, on the right-hand side. And I talked about the Big Bang, and we talked about time now here. And we talked about also that the first stars appeared about 300 million years after the Big Bang. So there was this first generation of stars when the clouds of gas compressed, became a star, lived for some time, exploded as a supernova or a planetary nebula, and then threw out all its gas out, threw everything out, and released its elements and metals into nature, into the environment. Okay, so this is what we call as the first generation of stars. Now, these elements, which is here, of course, these stars did not use all the gas. There was still hydrogen and helium. These stars fed the second generation of stars. So again, you have the same process, gas clouds, now but with more elements and metals enriched. They form stars. They live for some time. They explode violently. And again, they throw out their metals in space. And then you have then the third generation of stars. So if you could think of, so this would be, this is 1 billion years after the Big Bang. This is typing error here. 1 billion years after the Big Bang. So these are polluted by the first generation. And generation 3 now would be still some time later. Would be, let's say 3 billion years ago, around this time over here. And these are polluted by the first and the second generation. And they live for their time and the elements are being released. And our sun belongs to this third generation of stars. Our sun belongs to this third generation of stars. Our sun would be was almost born about close to, I would say, close to 9 billion years ago. Okay, close to no, so yeah, close to about 4 or 5 billion years ago, our sun was born and belongs to this third generation of stars. Now, what you understand is that you really need these three generations of stars to produce all the elements and their abundances on Earth. You couldn't do it with one generation. And then finally, you have life, which is starting here on Earth. And we know that life started 3.5 billion years ago on the Earth, okay? Because we have fossil records of this. And this reminds us then that the only way life could start on Earth was because of these three generations of stars. This is important to remember. So in a sense, we are made up of cosmic stardust. If it was not for these stars and their various generations, life would never have started on Earth. So in each one of us, I like to point out this little transcendental element. Each one of us is made up of stardust. And things which happened millions and billions of years ago and millions of kilometers away contributed to making us who we are. So this is the first thing which we talked about, the life of stars and the origin of the elements. This has been the major feat of the 20th century, to explain where do we come from. Let me now talk about this. So now this would be the fourth big idea of the 20th century. And this idea has something to do with the end of the universe. So yesterday, when we talked about the universe expanding, we realized that the universe started at a single point and was expanding, and we are living around at this particular time in time. So the universe was much smaller and slowly becomes bigger and bigger and bigger. And the natural question comes is, yeah, okay, the universe is expanding. We extrapolated backwards in time and we came to the Big Bang. But wait a second, can we extrapolate in the future? Can we extrapolate in the future? What is the future of the universe? Will the universe continue to expand, or will it slowly, fall in back on itself? Will it continue to expand forever at a constant rate, or will it, become an accelerating universe? That means it expands faster and faster and faster. The best way to think of this is, in terms of illustration, is like, think of a young boy, a very strong young boy, takes a ball and throws it up in the air. Okay? He throws it up in the air, and this ball now is rising. Now, depending on his strength and the force he uses, this ball can have three possibilities. It can either go up, rise to a certain point, and then stop, and then come down. Something which we are quite used to. It could also be that the ball, if this person is very strong, think of a rocket, could continue to go up, and never stop. Further, if it was, now think of a very fast rocket, those little rockets which take things into space. And as you know, rockets, they have their own fuel. And as they go up, they become faster and faster and faster and faster. And they're accelerating. Okay. So the question comes is, what is the fate of our universe? Will it continue to expand? Will it fall in back on itself? Or will it accelerate forever? This was one of the biggest questions of the 20th century. Around 1990, we were able to find the answer to this question. And it's very simple. So yesterday we talked about distances. Let me just give you some background first. We talked about distances. We realized that we could find distances to various galaxies using something which we call as standard candles. Yesterday we talked about Cepheid variables. These are certain types of stars which whose luminosity keeps changing with time. And we know that they are always going to be that bright, these stars. And therefore, we can judge how far they are. Now, there is another type of standard candle, which is called as a supernova. Now, just remember, supernova is the death of a star. So when the star dies, it explodes and becomes very bright. So you can see to very large distances, these supernovas, to very far, far away. And they also reach a certain brightness, which is fixed, and therefore they become a standard candle. Okay, the supernova becomes like that. Just to refresh your imagination, we used some imagery yesterday. Let me use another imagery today of what is a standard candle. Think of you as a captain of a ship off the coast of Goa, and as you are guiding your ship towards the coast of Goa in a storm. Think of the monsoons. You quickly see the Sinkeri tower, which is the lighthouse, the Sinkeri lighthouse, and you can see this light, which is very periodic. But you immediately, as a captain, you immediately realize, oh, this is a lighthouse. Lighthouses, you can see it's moving. The light is moving. It's rotating, and you may know most lighthouses have standard ways of. Most of them are uniform brightnesses. The way they shine are more or less uniform, and therefore you can more or less judge your distance from the coast and avoid being shipwrecked. Standard candles are like these lighthouses. So these supernova in the 1990s. People started observing supernova to large distances. So they're going out to really large distances, so really fast. So look at this side of the thing over here. So these are supernova which are very close. These are supernova which are very far over here, relative distance. Okay? And also they were looking at their particular, the age. So this where they are, or you can even talk about velocity. Well, what they realized was that there would be, I hope you can see that there would be three possible lines. There would be a universe where it would slowly decelerate, it would become smaller, so it would course itself, and that would be the blue line. There would be a straight line, which would be the universe is expanding at a constant rate, constant velocity. That would be the black line. And if it became a bit faster, it was increasing, it would be accelerating, an accelerated expansion. So just remember, yesterday we talked about expansion. Today we are trying to quantify that expansion. Is it the expansion is constant? Is it decreasing? Or is it becoming faster? Is it accelerating? And using these supernova, they realized that it more or less fit the red line, which meant that the universe was accelerating. That means the universe was expanding at a faster rate, which means in the past, the universe was not expanding so fast. Now it's expanding more, but in the future, it will expand even more faster. And there was nothing in their minds which could explain why this is so. But this was what their observation said. And therefore, they realized there must be something out there which is actually pushing things apart, a repulsive force. So we know gravity. Gravity pulls things together. But no, this thing is actually pushing things apart, repulsing galaxies from each other. It's as if, the galaxies had their own power source, like a motor within them, which was pushing them away from each other. So this is a big discovery in 1990. And the three people who discovered this actually even got a Nobel Prize for this discovery. And so from this understanding, we realize that we can talk about what is now called as the composition of the universe. Now, I'm going to make a quantum jump between what I said before and what I said now. So I said the universe is now expanding, not only expanding, accelerating. Okay, and based on the amount of acceleration which people detected, they realized that there must be something which is pushing things apart, and they called it, for now, they called it, because they didn't understand what it was, they called it dark energy. Okay, they called it dark energy, and they realized that it made up, whatever this thing was, we don't know what it is, it makes up about 68% of the universe. And everything what we know, what we can see, which is shines, is really a very small part, which is only about 5% of the universe. Let's leave this dark matter aside for now. There are things which we cannot see, which are not shining. But this is really more or less what is shining. It's like matter which we know it. Stars, supernova, brown dwarfs, black holes, gas planets, all this makes up only about 4.9% of the total budget, energy budget of the universe. But this is 68.3%, which we don't know what it was. We're still trying to find out what it is, but we call it dark energy. And dark energy is responsible for the acceleration of the universe, not the expansion, the acceleration of the universe. So let's try to understand what this is, okay? To make this concrete, this may seem abstract to you. Think of a big tug of war between two forces. One is gravity. Gravity is trying to, pull things together, make it compact. Dark energy is trying to push things apart, okay? And over time, these two forces are doing a tug of war. But what we have realized from those measurements of the supernova and that Nobel Prize which they won for it, is that this dark energy is getting stronger over time. And in the future, it will win. In the future, it will win over gravity. So what does this mean? So yesterday, I showed you a plot, an image where I had a Milky Way over here, and I had all the galaxies moving away at a constant velocity. I'm now trying to modify this imagery a slight bit to incorporate this understanding of gravity and dark energy, or an expansion and dark energy. So yes, if this is the Milky Way, galaxies further away are moving away from us. But close by to us, gravity is winning. So, gravity depends on distance. The closer you are, the more the gravitational force. So galaxies which are closer to us are actually being attracted towards us. But if a galaxy is far away and the gravitational force is very little, dark energy is certainly winning in this part of this. The expansion and dark energy are winning over here. So you have a strange thing. Galaxies are falling into each other locally, but galaxies further away are expanding. So they are moving away from us. So which is true then, as a question was asked yesterday, Andromeda, our closest galaxy, is falling towards us. The Magellanic Clouds are also falling towards us. But galaxies further away, which is like maybe 10 parsecs away, 5 parsecs away, all of them are going away from us. And in these galaxies, also galaxies are falling into them, but everything is slowly moving away from us and getting faster over time. What does this mean? It means that if you extrapolate this in the future, the universe will slowly become dilated. It will become dilated and dilated. And that will be the end of the universe. Okay? That will be the end of the universe. A slow dilation where everything will get very far away from each other. First, to complete the picture, the universe starts with a Big Bang. Let's not worry about this. You have what is called, where there are the dark ages, where there is no stars. Slowly stars are being formed. You have various generations of stars. You have the formation of galaxies and planets. And now there was a constant expansion. Now it's becoming faster and faster and faster. And slowly will become faster and faster and faster and expand. The fate of our universe is that it will expand into nothing and dilate and become just a big mesh. This is what our present theories tells us about the fate of the universe. We must also remember that our own star will soon die within 5 billion years ago. It will become a red giant. It will grow in size and start sputtering. It will destroy the Earth, and that about 5 billion years from here. Within 7 billion years, Andromeda will come and bang into us. And it will be almost catastrophic. But on the whole, the full universe as a whole will slowly expand and become a diluted mess. So this is now the future. Where are we going? This is what we now think is the future of the universe. Let me now move to the last most important discovery of the 20th century. And these are called as the extrasolar planets. Now, we have in our solar system a large number of planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. These are called as the planets. We kind of excluded Pluto. There was a question yesterday about what about Pluto? If you remember the figure I showed you yesterday in the previous PowerPoint presentation, I'm sure there were much more than just these 9 objects which are here in this figure. There are also things which are called as small objects which are not as big as the planets. And these are called as planetoids. Pluto was demoted because it behaved more like a planetoid. It did not behave like these planets over here. What most interesting is that these planets are divided into 2 parts. We call as the terrestrial planets and what we call as the Jovian planets. The first 4 are the terrestrial planets, Mercury, Venus, Earth, and Mars. And the other 4, Jupiter, Saturn, Uranus, and Neptune, are called as the Jovian planets. Or the Jovian planets are also called as the gaseous planets. What does this mean? It means that these planets, these first 4 terrestrial planets, have a solid crust. There is a crust on it. So if you land on it, you will hit you will touch ground. On the other hand, the other planets are much more massive, the Jovian planets. They're much more large, and they're actually made up of gas. The same gas which makes the sun, but they are really that small that they do not ignite and become a star, but they are really massive. So there are various types of planets, terrestrial and Jovian planets. So this is the solar system, our solar system. But also studying our solar system, we have realized many things. We realize that certain planets are actually suitable for life. We know that Earth is suitable for life. We probably think that Mars was suitable for life many years ago. But there is planets which are habitable. Okay, so it means a planet could possibly host life. And there are many things which are important for a planet to host life. First, it has to be terrestrial. So it cannot be a gaseous planet. It has to be solid. Second, it can't be too close because it will be too close. It must be close to a right type of star. A star like our sun is ideal. Anything else will either be too hot or too cold. If the planet is too close to the sun, to the star, it becomes too hot and therefore cannot support life. If it is too far away, it becomes too cold and everything becomes ice. Okay, so that's the thing. It also cannot be close to because there are a whole bunch of asteroids. It cannot actually be close to a large planet because these large planets cannot deflect asteroids close to you. So we're also very far away from the asteroids. We don't want asteroids falling onto the Earth every now and then, destroying life on Earth. So we realize that to have a planet which is capable of hosting life, we needed to be in a habitable zone. Sometimes we call this also called as the Goldilocks zone. Not too close, not too far. Now, the big discovery is we knew about our planets within our solar system, but what about other stars, stars far away? We have billions of stars within our galaxy. What do these stars also have planets? Now, if you can just imagine, look at the night sky. The stars are so small; they're shining bright, but they are very small to the naked eye. The telescope, the star is more or less like a point source. The question comes is, how would you be able to detect a planet around a star which is so far away? And remember, planets do not shine their own light. Only the star does. So we were unable to detect planets in other stars, partly because our telescopes were not able to detect anything. Our technology was not advanced enough. It was only at the end of the 20th century, towards the end, when our telescopes became bigger and bigger, and our technology became bigger and bigger, that we be able to actually begin to detect planets on outside our solar system, around other stars. So it's a massive jump in technology which has able to it. The techniques are very simple, and I will briefly explain to you a few of them, but the technology is very difficult. The first one is, let's try and hunt for these, what we call as exoplanets, planets outside the system. Think of a star and you think of a planet moving around that certain star. And if you observe the brightness of that planet, the brightness of the planet will slowly dip, will suddenly dip as the planet is passing in front of that star. And then when it leaves the line of sight, it will become, the brightness of the star will return back to its original. So you can detect this very small dip in the brightness of the star. And this we call as the transit method. So you really have to detect a small change in brightness of the star. Our technology has become so good now that we can actually detect these small changes in the brightness of the star. So we have found planets using this method. Another way of doing it is to actually detect a wobble. So if you have a planet, so you have a star and you have a planet revolving around it, the center of mass is no longer the center of the star, but it's slightly off off the center of the star. So in a sense, the planet revolves around the star, but the star itself revolves around the center of mass. So what do you see if you look at that star and it has a large, massive planet around it? The star will have a certain wobble. You can see this little wobble over here. And this wobble, as it is moving, as the star is slightly moving, is a change in the position of the star, this wobble, because there is a massive planet also revolving around it. And if you can detect the small wobble in the change in the position of the star, and with advanced technologies we can do it, you can find and detect a planet. Another way of doing it is also the same. Instead of looking at the wobble, because sometimes the wobble is too small to detect, you can detect actually the change in the frequency, the light of the star. Because as the star is revolving around that center of mass, it's moving towards us and moving away from us, moving towards us, moving away from us. And the frequency of light changes, as we talked about yesterday, the Doppler shift. This is another way of detecting exoplanets. The third way, perhaps the most difficult way of doing it, is especially for stars which are very bright and close to us, is what is called as the direct imaging method. And the direct imaging method is to look at the star and to kind of block out its light. And once you block out its light, you can see, things around it, and you can detect its planets. The best way to imagine this is like, you're driving in a car the sun is shining in your face, you lower the shade just to block off the sun so that you can see further. Okay, all of us have this experience. We kind of, as you're driving in the car, we lower down that eye shade so that we can block out the sun so that we can see further. It's the same sort of technique. You take your telescope, you kind of block out the light of the star, and then you can begin to see the other things which are shining because they reflect the stars, they reflect the light of the star. So there are now these various, I outlined some various techniques, and I'm going to show you a plot, which is the number of detections of stars which we have made through various techniques. Let's not worry about these techniques. But you can see right around 2000, we started detecting stars, not before planets around other stars. And with the increase in technology in the last few years, with the techniques, this has exploded. This has exploded. Today, we have detected nearly 4,000 planets around other stars. And 2 years ago, or even this year or last year, the Nobel Prize for Physics was given for the first detection of planets around other stars. So we have about now 4,000 planets detected around the stars. And this, remember, these stars are not very far away. They are quite close by to us within our galaxy. Now, something made news in 2015. Surely you may remember this. A star which is called TRAPPIST-1 was discovered with 7 planets, which very much resembled the Earth, all of them. They were kind of revolving around this star, which is called as the TRAPPIST-1. And some of them were even selected as potential candidates for hosting life. They were living within the habitable zone. Okay, this made great news in 2015 and 2017 between this, because first they discovered 3 of them, then they discovered the other 4, and the system is quite close to us, so we can study them further to detect planets also. We also now can look at the temperature of the star and look at the energy received by the planet and ask which of them is living in the habitable zone. Which of these 4,000 planets actually are capable of hosting life? They are terrestrial planets, they live in the habitable zone, they live around a star which is not too hot, not too cold, and could possibly host life. And this is an older plot from 2017, but this is being updated every year. And right now, there are much more candidates which are found. So right now, I tried to look it up. This was in 2020. This were some of the candidates of the star some planets which are most potential for hosting life, exoplanets which are potentially habitable, which could potentially host life. And this is a brief representation of the size of the planet. You can compare the sizes with that of Earth and Mars, and you can see that the sizes are more or less. And you can see how far they are away, 4.2 light years away, up to about 900,000 light years. So not very far away. Something which perhaps one day we could even hope to reach one day. But let me talk about what is now many of my colleagues are trying to search. The next step for my colleagues is to ask the question is, can we detect whether these planets have life? And the best way to detect it is to look at the atmosphere around the planet. They want to now look at the planet, okay, which they have now narrowed down their search, and they want to study its atmosphere. And the understanding is this: if there is life on those planets, then those life forms will produce certain molecules, okay, certain elements, water vapor, etc., which would indicate to us that it is possibly habitable. That is, not only possibly has life, it is habitable, but possibly has life. So now we have moved from studying the planet to studying the atmosphere around the planet. And the way we do it is to actually, the star, as its light is passing through, is actually passing through the atmosphere of the planet. And then we can detect what is there within the atmosphere of the planet by using the light from the star behind it, and to checking which molecules are present and which molecules are absent. And many of the next few years, the next 10 to 20 years, scientists will be looking, astronomers will be looking at studying the atmospheres of these experiments to search for molecules which could indicate life. And this is only possible with a great advance in technology. So let me now summarize. I've taken you on this whirlwind tour of the 20th century. And let me try and summarize what we have learned today. So we have learned three basic things today. First, we learned that the major triumph of the 20th century is to understand what fuels the stars. How are stars born? How do they live? How do they die? And around their lifetime and in their death, how do they produce the elements and their distributions? And we have realized that most of the elements are created in stars. The heavy elements are created in the death of the stars. And many of those heavy elements are important for our life. If we lack those critical vitamins, those critical elements, life would not be possible. And therefore, we realize that we are all made up of cosmic stardust. The second big discovery, which also got a Nobel Prize in the last century, is that we realize the universe is not only expanding, but it is also accelerating. And there is this repulsive force which is pushing things apart. And then at the end of the universe, due to this repulsive force, things will just dilute, they will overpower gravity and will become so spread out that nothing will be possible in the universe. It will die a slow death. And finally, the biggest discovery has changed our question of are we alone, which has tried to shed light on this question, where are we alone in the universe? Is thanks to an increase in technology now, we are able to detect exoplanets, planets which are around other stars. So far, we have discovered about 4,000 exoplanets, many of them terrestrial, many of them which also live within the habitable zone. And within the next few years, scientists will be working towards detecting molecules which will try and signal to us the presence of life in these exoplanets. I thank you for your patience, for listening to this very large, brief overview of the five big questions of five big topics, five big discoveries of the last 20th century. I will, once again, as I've done in the past, we've almost reached the time, it's almost 10 o'clock in Goa. I will try and answer these questions in written mode, because it's already crossed the hour. So I will collect these questions and I will ask the technical person at Collaborative Cafe to upload the questions and these answers. And I'll try to answer the questions to many things. You can ask me questions about yesterday, about today, but also things about things you have read and are curious about, especially about the universe and astronomy. Thank you once again for your patience, and I wish all of you a very good evening.
Thank you so much, Father. We have Miss Emilia who wants to speak a few words.
Sure.
A very good evening to one and all. I am Dr. Emilia Mascarenhas, retired Associate Professor, Department of Botany, St. Xavier's College, Mapsa. I'm indeed honored to propose, I'm indeed honored to propose a brief vote of thanks on behalf of the Collaborative Learning Cafe to Dr. Father Richard D'Souza, SJ, who is Goa's bright star, whom we are all very proud of. Thank you, Dr. Father Richard, for taking your valuable time off to talk to us over these 2 days. Your talks on both these days were very informative and explained in such a manner that anyone could understand. To Father Provincial Roland Coelho, SJ, and the Jesuits of the Goa province for their valuable work in our land and far beyond for the last 4.5 centuries. To every one of you who took their time off to make it to these sessions, where we not only learn but also honor our achievers. The CLC looks forward to your presence for its upcoming events. Let's make learning and knowledge sharing accessible, meaningful, and fun. Thank you and good night. Thank you,
Good night,
Father Richard.
everybody. Good night.
So for all those who want to access the answers and other materials like the videos and other things, like the slides, just follow what I demonstrate now. Okay, so you'll have to open a browser in your phone or maybe on your desktop and just visit our website, that is collaborativelearningcafe.org. The moment you open it, a small pop-up will appear. Okay, so this is the pop-up which you will get. You can directly click here and it will take you to the page where Father's content is already uploaded. That is both the slides of today as well as yesterday. And the answers to the questions of lecture 1 is uploaded for now. I'll be uploading the answers for the today's lecture, that is lecture 2, maybe in some time or maybe tomorrow. Here's the video which is shared, which has the whole recorded session of yesterday. You can access it. I will upload the today's lecture as well beside this. So please visit collaborativelearningcafe.org and through that pop-up you can reach to this place, or through this resources come to notes and videos, and then you can select Father Richard's talk and you will land up to this page. Thank you.